Welcome. This is Philip Schlump for the 1015 podcast. And I think this is an unusual title in a computer class to start out with what you can't do with computers. But you know, over the years, I've been asked to do this in a professional capacity a number of times. So knowing what you can't do so that you can look at your boss and say, yes, but what you've asked me to do is actually mathematically equivalent to this unsolvable and mathematically proven unsolvable problem. So unless you've got some insight I don't have about the nature of the universe, I can't do it. It isn't going to work. Well, last time we talked a little bit about the history of Unix. It doesn't go back that far, 1969. This time we're going to go a little bit farther back into the history of computers. And this is really about a problem that people were studying around the turn of the last century in the 1930s called the decision problem. And it's about this system of logic called first-order logic. And this really does have something to do with computers because the solution was solved by hypothesizing a computer program. So in first-order logic, we've got a bunch of premises that we would like to say, in some fashion, is there some way to go from this initial set of premises to a final conclusion and prove that that conclusion is true? People were trying to solve that. They'd been working on it for quite a while, decades. And they'd spent a lot of time. And a student in England came along and solved it in a very simple way. And I'm hoping that I can explain this to you in a fashion so that you'll understand what that solution is, which would be a pretty amazing feat because this is one of the foundations of computer theory. And if I can pull that off, explaining it simply as a foundation of computer theory, that would be amazing. But the question really goes like this. Is there a test you can use to get from these premises to your final conclusion and say whether or not the premises that they entail the final conclusion, that does there exist a proof? This is the decision problem. Is there an answer to this problem? Or is there any kind of a system that you can devise that will do this reliably? It turns out that there's a way to go and ask this. And we can ask it about a computer program. And this computer program that we ask it about, we can phrase the problem in a different way, but then we can prove we got back to this original problem. And the phrasing for that problem goes something like this. Can I build some computer program that will solve this problem, given a set of inputs and the program? It gives an output, and the output is very specific. Does the program finish or does it run forever? That's all you're interested in. And in this case, finishing is good. Halting is good. Whereas going on forever computing this is bad. If we can build this magic program, this black box, that inputs and a program go in and we can say, yes, this program will analyze, do whatever it does on the inside, and in the end it'll say either, yep, this program will finish, or nope, this program won't finish. If we can build that, okay, then we can feed basically the decision problem into it, and we can get an answer. And we can know whether or not there is a solution to the decision problem. So let's suppose we got this program. And this is kind of a cool thing. You know, it would be handy. I mean, something that'll test our code for us and give us an answer as to whether or not it's going to at least complete. And that would be cool. Well, the person that came up with this was Alan Turing. In 1934, he did not even have a PhD yet. He had published this paper describing this, what we would call his Turing seminal paper on computable numbers with an application to the decision problem. He actually used a German name for this that I cannot pronounce. I promise you, I have tried repeatedly. I can't get it out of my mouth. And I can say a lot of weird stuff. But this is Entscheidungsproblem. Problem. Oh, that is terrible, and that's a mispronunciation. Sorry for that. In any case, yes, the halting problem. Now, you have to put in context that at this point in time, that computers were basically a set of people that sat down and did a set of computations. According to some process, they would compute something. And generally speaking, this was a bunch of women that worked together Okay? At the beginning of the space program, you'll find that we were still using this technique to do all sorts of computation for launching rockets in the United States in the 1950s into the early 1960s. So this didn't go away for a long time, but eventually these people were replaced by machines. So if you think about this still happening in the 1960s, when Alan Turing talked about this in the 1930s, the way that computers were done is you had a staff and you gave them a set of instructions. They followed the instructions and they did the computation. And this was mathematical computations, and that's how they worked them out. And that was a computer. The question was, could you give this set of people some sort of set of instructions that could be carried out by this human mathematical clerk working by rote that would solve this first-order logic decision problem? Did this exist? And this is kind of a strange question, and people had not solved it. Now, if you put it in terms of a computer program, what you're asking is, does any program exist that will solve this? And when you start saying, does any program, you think to yourself, well, there's got to be a program that solves this. I mean, how can there not be this thing? Well, let's try it with the program and let's see if we can do it. Let's say I've got a black box, and in this black box I've got an input and a program on one side, and out the other side it spits out an answer. The answer is either yes, it will halt, or no, it won't. That's the only thing it tells me. Now, I don't know what's in the program. It does some whiz-bangy thing. Now, let's take the original program, whatever is in there, and let's add a little piece to the end of it. Anytime it spits out a yes, we'll loop forever and never halt. Anytime it spits out a no, we'll spit out a yes. Are we good with that? I mean, it just kind of like convolves it. I mean, now instead of it giving us good answers, it always lies to us. And if it was going to be a good answer, it loops forever. So, kind of an odd program. But let's take this program in this box. Now, we've got this box that takes an input and a program. Let's shove this program into the input of our box. And let's feed it back to itself. Okay? And ask the question, does it halt or does it not halt? And by golly, what do you get? Well, if the program is going to spit out, yes, it halts, then it loops forever. And if it's going to spit out, no, it doesn't halt, it says, yeah, it halts. And that's a contradiction. You can't both have it yes and no at the same time. And so with this simple little trick of imagining a program and feeding it back to itself to ask, is it good or bad? Guess what happens? We find out that we have a contradiction. There is something fundamentally wrong with our system. And in mathematics, when you have a contradiction like this, and you can say, this shows that there is something fundamentally wrong with this entire concept, you have a proof by contradiction that it can't exist. Now, in and of itself, that doesn't prove the original problem. But Turing studied under a guy named Church, and they came up with the Turing-Church hypothesis that they later proved that, yes, the two problems are equivalent. That if you have this Turing machine, then you can solve the halting problem. And if you don't have the Turing machine, you can't solve the halting problem for any system of first-order logic. It doesn't matter. And consequently, they took this thing that mathematicians had been working on for a long time, and they proved it can't be solved. That was by 1936, and they had basically proven this. But along the way, what they had done is they had hypothesized in great detail how these machines could work. And along comes World War II, and they need a way to solve a different kind of problem, basically a code-breaking problem. The Germans were using this thing called Enigma. It was a machine with a bunch of gears that you rotated cranks, and it encrypted data. Some people in Poland had figured out how to crack Enigma with some degree of reliability. Not perfect, but a really good method. So they had computers, yes, people going through this process, cracking the Enigma stuff regularly. At one point, they were figuring that within 3 hours of them capturing a radio transmission that had been encrypted with Enigma, that they could know what it was that transmission said 99% of the time. So they had a way to crack Enigma. But then the Germans came up with a better encryption scheme. And this better encryption scheme wasn't so easy to crack. Now remember what computers did. They worked on math problems. Alan Turing had an idea for building an electronic system that worked on symbols instead. Not the bang on with the drumstick symbol. This is symbolic computation. And he applied some of those principles to the process of cracking this other code. And he managed to succeed in building a machine that could crack this other code. By 1942, this system was cracking 40,000 encoded messages a day, basically one every 2 minutes, something like that. And this system that they had built, instead of just working on pure mathematics, was using a whole bunch of things that it represented as symbols, that it processed through as symbols. Kind of like, computers use letters and text. So he had a system working for this. And it worked. That was the key piece. Now, most of the time, it was really good. Once in a while, it didn't work. But their basic ideas that they had come from their Turing machine that he'd used to prove this esoteric thing had evolved into a new kind of computation that extended the capability of computation in a vast way. After World War II, Turing would be one of the leaders in this new thing that he called artificial intelligence. Today we call part of artificial intelligence machine learning. But in this artificial intelligence system, and I'm certain you've experienced this, you could actually test whether or not a computer was doing the same job as a human. And he called it it's become known as the Turing test. And there is a completely automated version of the Turing test, which may not be a perfect Turing test, but at some website you go in and they want you to click on pictures of fire hydrants. Why fire hydrants? And the next time they want you to pick out stoplights. Okay? Or they give you some piece of text that's written with a funny background, twisted at an angle, and they say, what does the text say? Well, what those are is completely automated Turing tests, or CAPTCHAs. And what they're trying to determine is, are you a human or are you a computer? And in a Turing test, the test is to test whether or not the person is indistinguishable from the computer. Turing's argument was that at the point when you can't distinguish human intelligence from computer intelligence, you have actual, real artificial intelligence. That if you can't tell them apart, the computer's as good as the human. And in fact, most of what the human brain does is this set of things that basically is a whole big collection of algorithms and processes that the computer can mimic and do exactly the same thing. There's no difference between a really good computer and a human brain. In fact, the really good computer may be better. Now, that's the Turing test. And I think we're getting close to or have passed the point where you can actually build a Turing test. Where you can say, yeah, for this specific kind of thing, the computer can actually beat the human being. And it can demonstrate the same level of intelligence. It's not a general test that does everything. But within certain specific fields, we've gotten to the point where the computer has passed the Turing test. So this is one of his big contributions to the field of artificial intelligence. Now, he designed a computer that he called ACE that was basically supposed to do symbolic computation. And that computer was never built. It was way more complicated. They eventually built, by 1950, a simpler version of ACE. But the fundamental ideas that he came up with in computation are with us every day. For instance, we talk about floating point numbers. Those are numbers that have a decimal point. Now, inside the guts of the computer All it has is on and off electrical signals. There's no such thing as a floating point number. And the computer mimics the behavior of floating point numbers by keeping around different pieces of information and having a library basically that does this calculation. Now, sometimes, the library has been built into the hardware itself, and you have lots of chips that do that for speed purposes. But basically, the computer doesn't do floating points at all. It calculates using a library. Alan Turing invented the first floating point computation library. In the same month, he also invented subroutines and call stacks. Now, call stacks are something you've seen me use them, and I talk about, well, the function calls this, and this goes onto this frame, and we're looking at how it's building this up. That stack, that's one of his inventions. So, he's had an impact on everything we touch with computers. Now, I wish the Alan Turing story had a happier ending, but in the 50s, he was either killed by the British Secret Service or accidentally died or committed suicide. One of those. And I don't think we have a definitive answer as to which one it was. But a lot of the fundamental stuff that we deal with in computer science comes from his work and his research, and he was absolutely phenomenally brilliant. It's amazing what he did in a few short years and during World War II and the years after that. But he created the first, real path towards computers, came up with the ideas of symbolic computation, came up with artificial intelligence and stacks and calls and subroutines and floating point numbers. All of these things in just a few years. So that's kind of the little piece of history that I want to talk about. I think we should also, recognize that his contribution was absolutely critical to the success of World War II. And what he did made a difference in the entire world during that war. So, an amazing contribution, but two things I want you to take away from this. The first one is, you can't build a halting problem program. There are things you can't compute and you can't prove. That doesn't mean that we don't use computers to prove some really interesting stuff, but there are things we cannot prove using a computer. In fact, there are things we cannot prove at all, and we know that now. And that's from Alan Turing. The second one I want you to take away from this is that the University of Wyoming has a pretty strong program in computer science, and a good portion of it is theory. And why do we care about computer theory? Well, the reality of computers is this. If you get a degree here, I will guarantee to you that within 10 years after you getting a computer science degree, working in the field, that you will have to do a significant amount of retraining. You're going to need to know about computer grammars and formal languages and computational theory and regular expressions and state machines and all of these things that are theory. Because guess what? Computers change. You're going to have to learn new stuff. And that fundamental theory allows you to deal with, how do I approach this new language? What are its properties? How do I learn it quickly and effectively? And all of those things are critical to your long-term work in this field. Now, they may not strike you as the most important, and you go, oh man, I've got to take this math class, discrete structures, and it's so dull. I got out in the work world. I needed to do some formal proofs of some stuff for, Intel. And because I had discrete structures, because I had classes in computer theory, I could go, okay, I didn't pay as much attention when I was in school to this, but I've still got the textbook and I can crack it open and I can start working on this and I can prove what I'm trying to do here. And I can take that proof and I can use it and I can build it into the code that they need. And it paid its dividends. So these things will come back, not once, but over and over and over. And that's why there is such a strong emphasis on computer theory here. We have some amazing people doing computer theory research in our research lab. We're using formal proof systems to demonstrate that security is going to be satisfied, that we can prove that things work in a certain way. So we're using formal proofs and proof systems to prove useful things. Like, for instance, hopefully one day you'll be able to prove that that expensive purse that your wife bought is an original thing and not a counterfeit. And that's going to be set on top of the foundation of Alan Turing's lambda calculus that he invented all those years so long ago. So with that, let's go have some fun, and I'll catch you later.